next talk is accelerating HPC and DL applications using MVAPICH2 DPU library and XScale-AI package. And the talk will be delivered by Dr. Donglai Dai. He's a chief engineer at XScaleSolutions and leads company's R&D team. His current work focuses on developing scalable, efficient communication libraries, checkpoint and restart libraries, and performance analysis tools for distributed and parallel HPC and deep learning applications in HPC systems and clouds. He has more than 20 years of industry experience in different area, and he's been granted 10 US patents and published more than 30 technical papers. And he has a PhD degree from OSU. Welcome, Donglai.
Thank you for the introduction. Okay, just going to start with this. So we had an earlier live demo on Monday, and some of the stuff we showed, but with a different system node or different result. But overall result, you can see it's quite consistent. Okay, so here is my overview of my talk. So we started with an overview of my company first, because it's a startup, so some of you may not know. And then I'll go on with MVAPICH2 DPU, which provide high-performance MPI library solutions to leverage the technology, especially from NVIDIA DPU. And then I'll cover a slightly different package, which is a package called XScale-AI, which provide high-performance solutions to deep learning applications. And I will touch on a slightly new product on that, which we add the DPU capability. Okay, and then I'll conclude. So, as this company, actually, we as a company, we bring innovative and end-to-end commercial service as well as training and support to our customers. And currently, we provide commercial support to many of the MVAPICH2 related product, or even some of them are open source. So it's like a Red Hat type of thing for this part of the business. And then we have also provide a value-added commercial product like XScale-AI or this type. Okay. And by the way, MVAPICH DPU is also value-added because the DPU part is not open sourced from OSU's. And as a company, we're a winner of multiple U.S. Federal Department of Energy SPURT grant, which is a national grant actually given to small business for innovations as well as for bringing new technologies to the market. And we are a silver independent software vendor for IBM Open Power Consortium. And most of our stuff actually are applicable to be run and on IBM Open Power Platform, except for DPU part, which later on, once it's available on the Open Power Platform, we'll support that as well. Okay. So if you are interested, you can go to our website. A lot of stuff out there public. Okay, now let's move on to some of the specific details about our product. So I'll touch on the MVAPICH2 DPU first. And this library is based on MVAPICH2 2.3.6. 2.3.7 just released. So later on, we'll upgrade to that. Okay, so this is still that. The current released version of this library is February earlier this year. Okay, we're working on a new release, which have many more enhanced features, improved performance, so that it will come soon. And we support all features provided by that MVAPICH2 library of that version. Of course, the versions are backward compatible. Any earlier versions feature available there, then we're supported. Okay. Specifically for this one, as we discussed before, the DPU, we're used it for overlap offloading. And for this particular one, we're offloading MPI functionalities onto the DPU units. Okay, and mostly we're focusing on, we find it more effective to offloading non-blocking collective calls, collective operations. And I'll just touch on a few of them, which currently we already support. It's actually a few more, but I'm only going to talk about the important ones. Auto all gather and broadcast. Okay. And we can see significant, one of the means to achieve in overlap, offloading is try to achieve higher overlapping. And some of that we are able to achieve by 100%. Of course, this requires some of the restructuring to your existing code to use non-blocking collectives. And by the way, it requires expertise in the application domain as well as your communication domain's expertise, and see what is the right balance between the computation and communication, and still guarantee you get the right result and achieve the overlapping properly. Okay, because there need data dependencies or that type of thing is important, which is your understanding of your application. And so we can see this library actually supporting any of the mix of different type of collectives that we support. Okay, you don't have to just choose one and see that has the most important impact. And but as we show, some of the application depends on the application. They're not using every collectives available. Some of them use one type more important, more than others. So there are some parameters you can tune for that. Okay, and some of this result I'm going to show is related to the demo stuff. So you see the real thing that is actually running on the real system, giving you background. And here is I give you some more, because in the demo I only show limited things because of the interest of the time. So we'll show the demo, but here we have more comprehensive or scale up result. And in this one, we're showing the total execution time of a micro benchmark, OSU benchmark. The auto I stands for non-blocking. Okay. And as you can see here, we're showing 32 nodes. By the way, this is a result we tested on NVIDIA's HPC cluster. They're kind enough for us to do most of our research on that. Okay. And why that, again, that's why we're doing this at the early edge of this. Because as a product, it's getting to the market. We actually started at the very beginning of it. And now more people started using it. Some of the presentations early on, it has been used in Cambridge or other places as well. Okay. And so here we are only showing 32 nodes because that's the maximum we can get. And we showing 32 nodes as 16 ppm as well as 32 ppm. As you can see here, the improvement on the micro benchmark is noticeable. It's about 20% up and down, depends on different parameters, grade, as well as the size. And this one is, we're showing one application. This is one of the FFT, like I think only 2 o'clock back or something like that. Touch on this. This is one of the version of a P3D, one of the FFT, which is a P3D FFT. And we use this to try the real, this is a computing kernel. We use this as a real application on top of the library to use that. And we're showing different input to the matrix, because this is 3D. So we have 3 dimensions parameters. And as you can see again, here is 32 nodes, 16 ppn as well as 32 ppn. And we're fixing the compute resource and increasing the input compute program problem sizes. So every time we double one at one time, so your computation amount actually get doubled and doubled more than that. Okay, as you can see here, we are achieving sometimes about as the compute grid becomes bigger, normally our improvement is more noticeable. And as you can see here, we actually see the end result. The application is getting benefit up to 20 plus overall performance improvement.
I was wondering if you consider to compare MVAPICH to DPU with other subversions of MVAPICH or like other MPI libraries to compare. So the base model here is MVAPICH2. And I'm asking, like, have you considered to use other, like maybe MVAPICH2?
Oh, you mean
like
compared to other library, MPI libraries? Yeah, the base model. We're comparing this is because it's easier for us to compare exactly the same parameters, okay? With the only difference is whether it's offloaded or not. Okay, because different libraries, you compare different parameters for optimization. Okay, so just a moment. So that's why we're doing this. So it's pure offloading features compared to that. By the way, Intel one sometimes performing better, other times performing worse. But the parameters you need to adjust for different runs. Okay, but it's within single-digit percentage of the difference from performance perspective. Normally, it's I think it's about 2% of difference.
Thank you.
Yes.
Sure. I just want to confirm, like, so the offloaded components are just like for communications, not actual computing.
That's true. We actually, when you do the communication like IOTA, there are processings. Okay, you can consider that as a part of the communication, or is still processing power involved. Okay.
There is one element here which is not fully optimized in a sense. So in the testing here, they still copy the data from the host memory to the DPU.
Yeah, actually,
not necessary, right? So there is a capability of the DPU to actually access the host memory directly. So that's kind of the next iteration that is trying to do with MVAPICH to be able to actually save the copy of the data from the host memory to the DPU memory and then run the non-blocking operations. Actually be able to keep it there and have the DPU move it directly from the host memory. So you should expect another level of performance improvement.
Yeah. So that's what NVIDIA and Glad's team is working on, is so-called unified memory. So what happens is the host as well as the ARM core on the DPU node can access the memory on both sides of the memory.
So similar to the Kunamalak managed, like similar architecture with the unified memory access in GPU.
Well, there will be iterations, but with the current Bluefield 2, Bluefield can access the host memory completely bypassing the CPU.
Oh.
Okay, so in this approach, what was done here so far is that you take the data buffer from the host memory, copy that to the DPU memory, and then have the DPU execute the
communication related to requirement, the operations.
Right,
yeah.
but you can actually keep the buffer there, move the non-blocking auto operations, and the DPU actually will take the data directly from the host memory and send it out to the other side without the need to copy that in the DPU. So there is actually a copy that you can save here in this one.
Yeah. So
Now, in
we,
future generations of DPUs, there will be more coherent access to CPU memory or GPU memory, but it's Bluetooth 3, Bluetooth 4.
yeah. We definitely expect another gear of this, okay? Once NVIDIA enable us to do that.
Thank you.
And this is for a different type of collective. It's IO gather. Okay, again, I'm only showing the overall execution. On the other day, I actually showing the overlapping on other features. Okay, so this is overall application. And we show 1 ppn and 16 ppns. A similar result you can get for larger ppn counts. Okay, and as you can see, here is even more. It's one of the reasons is because of the IODO actually have a lot more processing you need to do rather than just moving the data. And ARM core is relatively slow compared to the host. Okay. And this is for IBcast. We're trying this, just show the result on 16 nodes. Okay. And actually in the demo, we show that on 32 nodes. And again, the improvement is quite significant. Okay, now let me switch on to the next package, which is XScale-AI. This is a toolbox or a toolkit for accelerating deep learning applications. And so again, it's built on top of the MVAPICH2, and actually here again, the same version 2.3.6, okay? And it support popular deep learning frameworks, because this package basically including those ones, and including TensorFlow, PyTorch, MXNet, etc. And it integrated profile visualization tool for performance debugging, okay? And I'll show an example of that. And it also integrated efficient checkpointing, restart capability, and including this targeted for both CPU-based as well as GPU-based deep learning applications. And the other thing we find out, deployment of deep learning framework normally takes some effort to achieve. And if you use our package, we achieved single-click out-of-box optimization for your targeted system. Okay. Of course, this is tailor-made. Each time you order, we tailor-made it for you. Go ahead.
So what is deep introspect doing inside? Like, how are you optimizing deep learning applications using deep introspect?
Okay. Let me go through that. Then we potentially can come back with that deep, comprehensive question. Okay.
Okay, thank you.
And so, like I mentioned before, this package supports both open power platform as well as x86 platform. And its network we support InfiniBand, Rocky, which is the Ethernet, as well as the MVD. And here is one of the two examples I'm going to show. Okay, show out-of-box performance for the target system. Here is the target system. I'm not going to bore you with the details, but this is one of the things used at SX Max. Okay, and here it's 2 GPUs, no, 8 GPUs per node, and we're showing 16 GPUs. Okay, this is for small scale. I'll give you an example of a large scale application later. So this is 16 GPUs. And as you can see here, the improvement using this is using ResNet. Yeah, okay. As you can see here, the application, once you achieve that, it's still quite significant. Of course, this is after we targeted doing all the optimization for them. And this is another one which has a slightly different node organization. It's 4 GPUs per node. This is 4 nodes, again, up to 16 GPUs. And as you can see, the same trend remains. It's noticeable improvement on the overall performance. Okay, so you don't require application to change anything. You basically use this platform, and as long as we have optimized, optimized for you, built purposely for you, you will see this out of box. Again, this is the latest we can get. NVIDIA has the next generation to the market, so and double this, we'll see even more better results. Okay, and here I'll touch a little bit on the visualization part, which help you to debugging your performance. And this is basically a graphical interface for that. And as you run, if you find some problems, this will capture almost all relevant information on computation and the communication, especially with the communication part, which help us to do a lot of tuning on that. And I will just give you a few examples. So this is running on 1,000. I think it's running on 1,000 GPU here. How do I show that? But anyway, you can see prompt MP is 1,000. Okay, 1K. And here we basically recording most of the communication characteristics of distribution on what message. This is particular for one of the important one. We collected this for all the MPI operations throughout the entire execution. And here, as we know that all reduce is one of the most important collective operations, especially for deep learning, where you do epoch. You do this redistribution of your current going backward, propagation backward, doing this at the end of epoch. So this is a distribution of the latency. And this is a distribution of message size. As you can see here, it's showing 2 things. First is it's actually going up quite a bit. Okay, a lot of application message gets sent there. Okay, and so this is one example, and we show that how do we use not how do we use, what we achieved. Okay, how do we use? We have more expertise you need to build up. But as the end result, if you use this correctly, you can see you tuning this application. This is out-of-box performance, the blue bars. Okay, and this is after use our visualization tools to tune it properly. This is what you can achieve. And the gray ones are the idea, theoretical scale up thing. Okay, go ahead.
Very good result. So how are we optimizing it? Are we tuning Horoward or MVAPICH2? Like
Okay, now let me
run-
answer you this with this particular example. This is going to, Quentin can correct me if I went wrong. Okay, basically, based on whatever we analyze, there's 2 things for this application. It's all related to fused. What is that term? Yeah. Fused. Yeah. Horoward. Yeah. Tuning Horoward parameter.
So is it
So-
fused buffers and Horoward cycle time? Is it fused buffers, Horoward fused buffers, and
Yeah.
cycle time?
Yeah, actually, there's 2 things important here. It's basically the fused buffer. One is the buffer limit, the size. The second is the timeout. Okay, we basically adjust those. We increase the buffer size as well as increase the timeout a little. Okay, then we're able to achieve this.
Can we use it to optimize communication runtime, like the communication runtime level parameters? Because
Yes,
the last
and
info-
next one we will show you that.
yeah.
This one is a communication runtime. Okay, And that's the inside. Okay, I'm now going to show exactly what we adjust. But this is what we're able to achieve using that tool, because we have the characteristics of what happened during the communication. And this is, again, focusing on high auto reduce, because that's the most dominant one for this application. Okay, and before we, out of box, we're achieving this one. And that's only about 50%. And after you do a proper tuning based on whatever the information we're able to gather, we're achieving this one, which is fairly close to the ideal speed up. Okay?
Thank you.
That answers your question. Hopefully, when you ask more, I can give you more concrete. But as you can see, the information you use, you are able to gather, but how to use it, you need some expertise to do that. And so here, I'm going to touch a new features we add in. So this is a checkpointing. And this is checkpointing built in this package. And it's this capability, we leverage the open source SCR library from Livermore lab. Actually, Adam is the leader of that team. Okay, he has been working on this for years, and we're leveraging that and build whatever we proved to be effective in this package. And we're supporting applications, checkpoint for any DL applications which use the platform we support. Because we do that at the platform level, which is your DL model will use that platform, you will get that automatically. You don't have to pay much of attention of it. Of course, again, if you go through some of the parameters we need to adjust, you go through that visualization tools, again, to do the adjustment and analysis, okay? And I'm going to show you two examples of this two particular DL application. One is ResNet, which more or less serves as a benchmark. And the other one is a single image super resolution. Okay, both are image related. And one used, actually, we did this for both of this platform. One is a Harvard over PyTorch, or Harvard under PyTorch, depends on which way you look at it. The other one is using the PyTorch distributed data parallel model. And this is one of the application, which is ResNet 50. And as you can see here, this is up to 128 GPUs. And we can see that the overhead, okay, one of the concerns for scale checkpointing is how much overhead in both execution time as well as disk space, okay? And here we pay attention to the overhead on the application execution time. And disk space we can talk about later, because that's one of the strengths of a scalable SCR. Basically, it is scalable on the storage to save the disk cost. And as you can see here, with this enabled, there is a default built-in checkpointing capability for those the open source framework, the deep learning framework. Okay, but as you can see, this green line is the default one, and the blue one is whatever we are able to achieve for this application. Okay, as you can see, as this goes big, the benefit is really dramatic. And similar things for the next. Huh? It doesn't move?
No, like you have to use.
Which button?
That will not be visible on screen.
What did you do? Oh, you repointed. Okay.
Ask a question. So are these overheads just for runtime or overhead because checkpoint restart?
Can you say that again?
Oh, sorry. Are these overheads just for runtime, no checkpoint, no restart? Or it's
Oh,
because
this is for looking at the checkpoint itself.
okay, second.
Yeah, looking at the checkpoint itself. So this, what we say, this is a checkpoint overhead itself. And this is for the other application, okay? And we can see it's achieving similar result. So most like this, right now it looks like a flat. We as we go up, this is actually slowly moving up, okay? But it's more like a log n type of thing rather than linear or exponential. Okay, now let me touch the latest one. We're able to use the DPU technology. So this one, it's overall functionality is trying to achieve the same thing, to speed up the deep learning applications, but by using a DPU for offloading some of the functionalities to the DPUs. And what exactly part we're offloading, and right now we're starting to offloading, especially pay attention to the data loading or other stuff, which have shown significant benefit. And we also work on different parts as we develop more stuff, okay? And so right now we're supporting PyTorch related stuff, and TensorFlow currently is under we are not assuming, we're working on it to make it sure that it works properly. But the approach is similar, okay? And so again, we work on the deployment problem for this. So this is the key result. And let me explain the result a little bit. So this is the overall execution time, okay? And right now we're only showing for CPU only because the system we have has the DPU on it. That system does not have a GPU, okay? So we're showing the CPU only computation model, okay? And as you see, the green bar is with the offload, okay? And red bar is without the offload. And the line of the blue line is the percentage of improvement in time, or you said reduction in time, and the percentage here on this side. Okay, it's right now with this particular application, as well as for all the parameters or system configuration, it's about 10, slightly more than 10%. By the way, we have result for larger system like Soren, and that we are achieving about 15% above that. Yeah. So this depends on the overall approach. Overall benefit depends on your application and machines we tailor to, but the benefit actually also depend on your application characteristics. And that's all. So I'm going to make a conclusion. So exponential, we are seeing, well, at least it's projected by industry that HPC and the AI market is growing exponentially in the decades ahead. And the critical thing is software for HPC and deep learning is lacking behind the hardware now starting to the market. And for us, we currently working on the CPU version, and we are working on, well, actually depend on which package we're mentioning, okay? most of the stuff work on both the CPU version as well as GPU versions. And GPU version right now, we're testing that out, showing that it worked out with NVIDIA's ones. We also work for the AMD as well as Intel ones. Once they are more available, we'll try to make sure they will be beneficial as well. But the scheme we're working on should have no problem with that. It just needs to be worked out with the real machine. And so we provide different solutions, well, different products to address this for high performance as well, HPC as well as AI applications. If you're interested, all this are licensed. So contact us. We give you a field trial license if you're interested. Thank you.
Any questions?